Okay, so in this video we will solve a problem on again rigid body kinematics, and I have drawn the picture here of the system. So essentially there is a disk that is rolling without slipping on a horizontal surface, and on the disk there is a slot, and that slot is at a distance of d from the center. The slot is along a straight line, and on that slot there is a point which slides along the slot, and that point is shared by a bar that is constrained to move horizontally. So this bar moves horizontally with a velocity of V0. It's a constant velocity V0, and the bar is at a height of h from the ground. The disk is of radius capital R, and the goal in this problem is to find out, as the rod moves towards the right with a constant velocity V0, what is the angular velocity of this disk, and associated with that is the problem of what is the velocity with which this variable x is changing. Now x is the offset of this pin, which is the connecting point between the slot and the bar. It's the distance of the pin from the center of the slot. So you see x is the distance of the pin from the center of the slot. So so that's the problem, and we are going to use a rotating frame to solve this problem. Specifically, we are going to use the cylindrical coordinate frame, r theta coordinate frame. So here you can see the radial direction is perpendicular to the slot from the center. So it's going to always remain perpendicular to the slot from the center, and the theta direction is perpendicular to that, and this should be EZ instead of EB. EB is typically used for normal tangential. We are using the r theta, or the cylindrical coordinate frame. So EZ is going to be in the direction of ER cross E theta. So if you curl your fingers from fingers of your right hand from ER to E theta, then EZ is pointing downwards. So that's the direction of EZ. So that's the problem. And in this problem we will have some application of constraints as well, that you will see, in addition to the three-term equation that relates the velocity of 2 points in any moving coordinate system. So we will do that so we'll solve that problem now. So let's first try to formulate the kinematic constraint that operates in this problem. And that kinematic constraint is that this pin is going to be always at a height h from the ground. Now the location of this pin can be expressed as the sum of the radius of the disk plus the vertical component of d plus the vertical component of x. You could say minus the vertical component of x, right? So that sum, so r plus the vertical component of d minus the vertical component of x, should give me h at all times. So that is a constraint that we will formulate first. So if you think about the center, so I'm going to just sketch it separately. The center, let's say, is at distance r from the ground, and at the center, let's say that this is the direction of ER, okay, and this is the direction of E theta, and ER makes an angle of theta. Now at a distance D, so this is at a distance D, you have the slot, and along that slot you go a distance x, okay, and that is the location of the point P, okay. So now we know that this location is at a height h, so we know that P is always at height h. So you can then say that therefore r plus d cosine theta plus, now let's find out what is the vertical component of x. So if you draw a vertical line parallel through this point, okay, then if this is x, then this angle is if this angle is theta, then this angle is theta, included angle, and then this angle then is 90 degrees minus theta, okay. So then the vertical component of x is going to be, or the negative of the vertical component is x cosine of 90 degrees minus theta is equal to h. So we can then effectively say that r plus d cosine theta minus x sine theta, because cosine of 90 degrees minus theta is sine theta, is equal to h. So this is actually one constraining equation or constraint equation which is true at all times, and we can use this. Now you can say that, can we not use this to find the velocity, angular velocity theta dot? Well, the problem with this is that if you differentiate, so if you differentiate this, you'd get negative d sine theta dot minus x dot sine theta plus x, or rather minus x cosine theta dot is equal to 0. So that's the total derivative of this equation. Note that r is a constant, capital R is a constant, so its derivative is 0. Note also that small d is a constant, so its derivative is 0. And hence, if you carry out the derivative of both sides of equation 1, this is what we get. And if you simplify this, what we get is the following. We get d sine theta plus x cosine theta dot plus x dot sine theta is equal to 0, right? So as you can see here, this equation, although it relates velocities, which is obtained by differentiating equation 1, it does not allow us to calculate theta dot and x dot independently. It is one equation with these two unknowns, so we have to use kinematics in this problem in order to solve for theta dot and x dot, okay. Of course, this equation means that given a x, I can always find out theta and vice versa. So x and theta are kind of related, are exactly related, and that relation is given by equation 1. Now you can see that x and theta are related because of the fact that this disk is rolling without slipping. So because it is rolling without slipping, what happens is that as this turns, in order to maintain the bar at this height, this needs to be moving at a certain this needs to move by a certain amount so that the height is maintained. In other words, you can say that if this bar is moving with a constant velocity v0, then that will force a certain angular velocity, and because the disk is rolling without slipping, that angular velocity will be such that theta and x will be related. So if you know x, you'd know theta, and vice versa. Okay, so with that, then let's get to the kinematics of this problem and solve it. So the equation that we will write, we are interested in finding theta dot and x dot. So this is a problem where you see that we have been using these equations, velocity of p is equal to velocity of c, and so on and so forth. Typically we have you come across problems where you want to find out Vp, where p is this particle. Here is a problem though where the Vp is given, okay, and for that matter Vc is also very clear. It is just theta dot times r, okay, and so in fact it is the Vc that is of a greater interest in this problem. But we know that the point C is moving along the horizontal direction. So let us formulate this and say that Vp is equal to Vc plus omega cross rho plus rho dot r. Okay. Now let us explain this. Rho is equal to the vector going from C to P. Okay. So rho is this vector, okay, and rho dot r is the velocity of p within the rotating reference frame. Okay, now let us understand this reference frame for a minute, how this reference frame is being defined. The r theta reference frame is it is fixed to this rigid body in this direction. So r is always going to be perpendicular to the slot, theta is always going to be parallel to the slot, and we are defining it such that its origin, or rather r is passing through the center. The origin of this coordinate frame is really not that important because will be directly working with velocities, so it's not important where we place the origin of this coordinate frame. So as the disk turns, r turns while keeping itself perpendicular to the slot, and theta turns while keeping itself parallel to the slot. And so when we say that rho dot r is the velocity of p within the rotating frame, what we mean is that within this rotating frame, as the frame turns, we want to quantify what is going to be the velocity of the point p as observed within this rotating frame. So if, for example, you were an observer that was let's say stationed here, and you were fixed to this disk, and you had one gaze in this direction and another gaze in this direction, basically you had a way to measure anything that is happening on the disk, but you don't have any idea of what is going on outside the disk, then what would you perceive as the velocity of the point P, right? And you can see intuitively that if you were part of the disk, if you are fixed on the disk, right, then the velocity of the point P that you would perceive is just the velocity along the slot. Okay, and that is what we are going to formulate when we get to this term. So this is the three-term velocity expression. Now let us formulate Vp. Vp is the absolute velocity of the point P. Now what is it? It is V0, and it is in the horizontal direction. So what is the but we need to express everything in terms of this coordinate frame ER and E theta, right? We cannot express certain things in ijk and certain other vectors in ER and E theta, because then we cannot do the vector summation. So all the vectors have to be represented in terms of one coordinate frame, and that coordinate frame is r theta in this case. Okay, so what is Vp? Well, to understand that, let's draw a horizontal line on this figure here, Okay, because we know that the velocity of the point P is always horizontal, so V0 is in this direction, right? Now if this angle is theta, you can see that if I draw a vertical line here, then this angle is theta. Okay, and if this angle is theta, then this angle is 90 degrees minus theta. So V0 makes an angle of 90 degrees minus theta with ER, and then it also makes an angle of theta with E theta. So V0 makes an angle of theta with E theta. Okay, so with that then we can easily then write Vp is equal to V0 cosine theta E theta plus V0 sine theta ER. Okay, so we have the expression for Vp. What is Vc? Vc is the velocity of the center of the circle. Now, the center of the circle also has a horizontal velocity, right? Because it is a horizontal surface and it is a disk. So as the disk turns, the center moves in the horizontal direction. And we don't need to do any kinematic analysis because this is simple enough. But we know that if a disk is turning with an angular velocity of theta dot, then the velocity of the center of the disk is going to be theta dot times the radius of the disk, right? So the velocity of the center is theta dot times capital R, and it is also in the horizontal direction. So you could go back to this diagram and you could also say here, put that the velocity of the disk is theta dot R. It's also in the horizontal direction. So Vc is also in the horizontal direction. So theta dot R cosine theta E theta plus theta dot R sine theta ER, right? So that's Vc. Now let's get to omega. What is omega? Well, omega is the angular velocity. Remember that when we are using a rotating coordinate frame and we write this relative velocity equation, omega always represents the absolute angular velocity of our rotating frame of reference. So in this problem, that translates to what is the absolute angular velocity with which this coordinate frame, this r theta z coordinate frame, is turning. And that is pretty easy to see because this coordinate frame is always perpendicular and parallel to the slot. As the disk turns, the coordinate frame turns with the slot, and so therefore with the disk. So the angular velocity of the coordinate frame is theta dot, and in fact it is in the z direction because it is going clockwise. So it is theta dot Ez. So here we have theta dot Ez as the angular velocity. Now next let's find out what is rho. Remember, rho is the vector going from C to P, okay? Because we are writing this velocity equation of P relative to C. So rho is shown over here, right? So this vector, you see, is d times ER plus x times E theta, right? So you can express it using these two unit vectors, ER and E theta, by saying that the vector rho is d times ER plus x times E theta. So d times ER plus x times E theta. So we have figured that out. Now lastly, we need to figure out what is rho dot r. So let's figure that out. So rho dot in the rotating frame. Now this problem is simple enough where you can, from the intuitive understanding of the rotating frame, you can formulate what rho dot r is. As we have mentioned, since this particle P, which is the pin connecting the slot with this horizontal bar, since this pin is constrained to always move along this slot, so if you are fixed to the disk, then the velocity of this pin that you would perceive, that is the velocity in the rotating frame, the relative velocity in the rotating frame would just be x dot e theta. X dot, because this is the only velocity that you would see, and e theta, because that's x is going to always be in the direction of e theta, so x dot is always in the direction of e theta. So you could say, just from an intuitive understanding, that x dot is equal to rho dot r is equal to x dot e theta. Now you can also formulate this in a more structured manner. And what is that structured manner? Well, that structured manner of developing this rho dot r is to take this rho vector and differentiate, but differentiate with the understanding that you are differentiating only within the rotating frame, which means that when you are differentiating within the rotating frame, you are not going to differentiate ER and you are not going to differentiate E theta, although ER and E theta are both changing directions. Okay, you would be differentiating, you would not be differentiating ER and E theta, and that would give you that process of differentiation, that special differentiation would give you the relative velocity within the rotating frame. So if you did that, you would get d dot ER plus x dot E theta. Right? Note that we have not done ER dot and E theta dot. Right? And that's because we are differentiating within the rotating frame. So d dot is 0. So what we get is x dot E theta. Right? So this is a more formal, structured way of finding out the relative velocity within the rotating frame. Okay, by not taking the derivative of the rotating unit vectors. So now we have formulated all the vectors. Now we can say that therefore Vp, which is, so therefore V naught cosine theta E theta plus V naught sine theta ER is equal to theta dot R cosine theta E theta plus theta dot R sine theta ER plus we need to now take omega cross rho, so that is going to be theta dot EZ cross DER. So let us identify our vector product. So you have ER, E theta and EZ. ER cross E theta gives EZ, and hence we form this convention of cross products, and this forms the right-handed coordinate system R, theta and Z. So with this coordinate system in place, then first we take the cross product of theta dot EZ with DER, which is going to be theta dot D, and EZ cross ER, EZ cross ER is E theta, and then we do theta dot EZ cross X E theta, so that is going to be X theta dot, and EZ cross E theta is minus ER, so minus ER. Actually I should put a plus sign here because this is just the continuation of that previous line, the continuation of the right hand side, and then we have to include the rho dot R, which is plus x dot E theta. Okay, so that's our overall kinematic equation relating the various velocities, relative velocities, and so on. So we'll go to the next page. Now, collecting E theta terms, we will have V0 cosine theta is equal to theta dot r cosine theta plus d theta dot plus x dot. Okay, so this becomes equation number 3, and collecting ER terms, we have V0 sine theta is equal to theta dot capital R sine theta minus x theta dot. Okay, so that becomes equation 4. So now we are all set, and we will be able to figure out these angular velocities and the angular velocity and the linear velocity x dot. So I am going to keep this constraint equation and the second equation in my view as I do the remainder of this derivation. All right. So from 4 we have theta dot is equal to V0 sine theta divided by R sine theta minus x. Right, so that's the angular velocity. Now you may wonder, well, I want my angular velocity as a function of theta, because what I want is, as this moves and as the disk turns, okay, what is my angular velocity with this movement, with this angular movement theta? And in order to do that, what we need to do now is go back to our constraint equation that we had written as equation 1 and substitute for x. So we have V0 sine theta divided by capital R sine theta minus x, and x is, as you can see here, it is R minus h plus d cosine theta divided by sine theta. So in other words, the angular velocity as a function of theta, that is, theta is the movement of this disk, or the angular movement of this disk, the angular velocity is V0 sine squared theta divided by R sine squared theta minus capital R plus h minus d cosine theta. So that's theta dot. And now you can find out x dot either using this equation, which is equation 3, because you can substitute for theta dot here and solve for x dot, or you can substitute theta dot over here and solve for x dot. Remember, equation 2 is just the derivative of equation 1, so both of them are valid. So I can now say that from 2, just move this up a little bit. So from 2 we have x dot is equal to negative d sine theta plus x cosine theta theta dot divided by sine theta. And so you can now substitute for theta dot. You could also substitute for x and find the solution only in terms of theta. This is x dot, by the way. So I'll just substitute for theta dot and then leave it there, because it's quite trivial to now substitute for x from equation 1. So minus d sine theta plus x cosine theta and theta dot divided by sine theta is going to be it's going to cancel one of these sine squared. So V is V naught sine theta divided by r sine squared theta minus r plus h minus d cosine theta. Okay, so that's the expression for x dot. Right, now one of the things that you may wonder is that, well, we just mentioned that we could derive x dot from equation 3, or we could derive x dot from equation 2, and we took equation 2 and derived x dot. Now what is the guarantee that the two x dots that we are going to get are the same? They should be the same if the physics is correct. You should not get two different answers if the physics is correct. So this equation 2 must not be a completely new equation. In fact, it should be, because it deals with velocities, this equation 2 should be derivable from 3 and 4. Otherwise you have created new information, which means that potentially x dot calculated from 2 and 3 are going to be different. That's not the case. Physics tells us in this problem that x dot has to have a unique value, okay, because everything is constrained. If I move the bar with a constant velocity v naught, I know what is the angular velocity, I know what is the x dot. Okay, so you should have a unique value. So to show that 2 is nothing but the information in 2 is there in 3 and 4, okay, you can do a small verification. So I'll do that now. So let me just combine equations 3 and 4 and show you what we get. So if you take equations 3 and 4, okay, and let's say what we do is we multiply both sides of equation 3. So let's do the following. So say we do the following. Equation 3 times sine theta minus equation 4 times cosine theta. Say we do this. What will happen is, on the left hand side, when you do the subtraction, you have v naught cosine theta sine theta minus v naught cosine theta sine theta. So they would cancel. So then we will have 0 is equal to, now if you are multiplying the right hand side also by sine theta, and of 3 by sine theta, and the right hand side of 4 by cosine theta. So when you subtract, these terms will also cancel. So what you would have is d theta dot sine theta plus x dot sine theta minus x minus x theta dot. So minus of minus x theta dot cosine theta. Or in other words, you would get 0 is equal to d theta dot sine theta plus x dot sine theta plus x theta dot cosine theta equals 0, and this is, you can verify that this is same as equation 2. Okay, so in fact let's put equation 2 here and show that they are indeed the same. Let me see if I can put everything. Yeah. So note equation 2. Equation 2 had d theta dot sine theta plus x theta dot cosine theta. So d theta dot sine theta plus x theta dot cosine theta plus x dot sine theta plus x dot sine theta is equal to 0. So we verify that indeed equation 2 has the same information as equations 3 and 4. So therefore equation 2 has the same information as in 3 and 4. So hence we have also verified that indeed the x dot velocity that we would have calculated if we used equation 3, for instance, would have given us the same answer, right? Because indeed the same information is captured in 3 and 4 as in 2. So that completes this problem, and what we have seen is a problem on, again, rigid body kinematics. You have a constrained motion in play here, and in addition you have a rigid body kinematics which uses the 3-term velocity expression, Vc, omega cross rho, and rho dot r. So that is it. That's the end of this video. Thank you.